Hello, welcome to Equity Education, the chemistry version. And today we're going to be looking at Hess's law and how to use Hess's law to calculate enthalpy changes of reaction and enthalpy changes of formation. Okay, so quite a lot of students find this quite difficult, so I'll try and keep things simple so you've got a clear understanding of what's going on. So I'd like you to open up your booklet and we will get started. Okay, so our definition, Hess's law. So we can describe Hess's law as the enthalpy of a reaction is independent of the route taken. So what does that mean? So we can draw a diagram to show this. So A plus B forms C plus D, and on the bottom let's have W plus X plus Y. Okay, so we have two different ways that we can get to C and D. We can go the top way, around here, so we'll call this route 1. Or we could go this way, which we'll call route 2. So route 2 goes through W plus X plus Y, so these might be intermediates. And what Hess's law states is that the enthalpy of route 1 will equal the enthalpy of route 2. So why is this important? Well, if we read the next bit, it will explain it. So enthalpy cycles are used to calculate the enthalpy change of a reaction which cannot easily be measured directly. So for example, maybe it's not very easy to form C plus D over here directly from A plus B. Maybe the activation energy for the reaction too high, the rate's very slow, we don't know. Yeah. So an alternative reaction is to go through W plus X plus Y, and that means if we can measure the enthalpy of route 2, we know what the enthalpy of route 1 is also. Okay, so what does that mean for you? So there are generally three different types of enthalpy data you will use to calculate the enthalpy change of a reaction. First one is calculating the enthalpy change of a reaction from bond enthalpy data or bond dissociation enthalpy data. I'll give you the formula for this, but this is also on another video, so I don't want to spend too long going through that. So next one, calculating the enthalpy of a reaction from enthalpy of formation data. And thirdly, calculating the enthalpy of formation from enthalpy of combustion data. Right, so it's important not to get these mixed up. Yeah, if you get them mixed up, you're going to get it wrong. It's also important to understand where it comes from. Okay, so using bond enthalpy data, all I'm going to do is just give you the formula for this. So if you're calculating using bond enthalpy data, it's the enthalpy change of the reaction, and it's the enthalpy sum of the enthalpy of the bonds broken minus the sum of the enthalpy of the bonds formed. Okay, no examples on that because that's not what we're really doing. If you look on a previous video, there's lots of examples and questions on that you can have a go at. Okay, so the important bits. Using enthalpy change of formation data. So if you are given enthalpy change of formation data, if we go back up to the top, means we're probably going to be calculating the enthalpy change of reaction. Okay, so let's do an example. What should we do? Okay, yeah, so I'm going to have a reaction, so C2H4 gas plus HCl gas goes to C2H5Cl gas. Now this is an enthalpy change of reaction. An enthalpy change of reaction can be anything. It's just the quantity of the reactants and the molar ratio of the quantities of the reactants forming the products in their standard states under standard conditions. So here we have ethene plus HCl and we're forming a halo alkane. Okay, so this is just an example. We'll go through a question in a minute. If you are given enthalpy change of formation data, it means that your elements in their standard states go on the bottom. So carbon, H2 gas, and Cl2 gas. We've only got one Cl, so I will have half there. And we've balanced everything else, I think. No, we haven't. 3H2. Is that right? No, 5. Whoops. So we got 5 hydrogens, not 6. So 2.5 here. Okay. So this is our bottom, and this is our elements. Now, enthalpy change of formation means what? Let's see if you can remember. I'll give you a couple of minutes, well, not a couple of minutes, about 10 seconds to think about what the definition of enthalpy change of formation is. Right, I hope you thought about it. So when we describe enthalpy change of formation, the enthalpy change of formation is when 1 mole of a compound is formed from its elements under the standard states and standard conditions. Yeah. So here is my compound, C2H4. We'll take this for example, and it's being formed from the elements in their standard states, the standard conditions. So carbon's a solid, and we've got hydrogen as a gas, which must mean from that definition the arrow must go up. So we're forming this. We're also forming this, and we're also forming this. And this is important when you're trying to work out which way the arrows go. So in this example, when we have enthalpy of formation data, the arrows always point up. And we can also say that the elements in their standard states are on the bottom. Okay, arrows are pointing up, elements in the standard states are on the bottom. Okay, and that means now we can use a formula to calculate this. So let's call this A and B and C. Okay, so if we're trying to calculate the enthalpy change of reaction, so on the top line, my enthalpy change of reaction must equal, now we've got to follow the arrows round. For this is our root 1, this is our root 2. So my arrow's pointing the wrong way. So I would have minus A. This arrow's pointing the wrong way, I want to go this way. Plus minus B. This arrow is pointing the right way, so plus C. A, B and C are enthalpy values for formation in kilojoules per mole. Okay, hope that makes sense. So I'll just go through it again. So our root 1 here on our top is equal to our root 2 if we're going this way around. We've had to change the value of A and B because the arrows are going the wrong way. Right, so let's think about this then. I'll let you have a think about this. So why do the arrows point up? Again, I'll give you a minute to think about it. Okay, so why do the arrows point up? I want you to have a go at writing the enthalpy change of formation for ethene. Okay, and you can use the value for the enthalpy change of formation as A. Okay, so I'll give you another minute to write that down. Okay, so from my definition, I'm sure you've all written this down. So when 1 mole of a compound, in this instance it's ethene, is formed from its elements under the standard states and under standard conditions. So we would have this, and then we need to balance it, so 2 here, and we give this the value of A. So this is my enthalpy change of formation. And all I have done in this Hess's law example is put it in a slightly different format. So here are my reactants in their standard states at the bottom, here and here, here and here. The arrow is going up, A, and it's going to the formation of my product. So that's why when you're using this type of data, the arrows are going to point up. Okay, hope that makes sense, because now you can have a go at it. So please have a go at doing this question. You need to draw a Hess's law cycle and calculate what the enthalpy change of the reaction is. Okay, I'll give you 5 minutes. Okay, right, we'll go through the answer then. So I've written this out again, I'm sure you have as well, and this is my enthalpy change of a reaction. So this is my enthalpy change of reaction. This is what I'm trying to calculate. Now I know from our example that I need to put the elements in their standard states on the bottom line. So that means I'm going to have hydrogen, H2 as a gas because it's already in its standard state as an element, plus carbon, so carbon on its own, and then I'm going to have oxygen as well. Okay, is it balanced? No, not quite. So yes, it is balanced. Okay, so it's balanced. I now know that I'm just going to put these arrows going up, so from the elements to whatever forms. As a side point, it doesn't matter if your arrows do not exactly match which elements you're using on the bottom, okay? It's just to show which way they're going. We don't need to put our arrow for H2 gas because it's just staying as H2 gas. Okay. Now we can calculate my enthalpy change of reaction. So my enthalpy change of reaction, let's write this about a bit more neater. So this is my enthalpy change of formation of CO2, and this is my enthalpy change of formation of, you don't know what this is, it's methanoic acid. Okay, so my enthalpy change of reaction, so the root 1, I'll show it a bit clearer, is equal to my root 2. You don't have to write this on, yeah? So that means that if I'm calculating my root 1 and it's equal to my root 2, this arrow is going the wrong way around. So my enthalpy change of reaction will equal minus delta HF of CO2 plus, this arrow is going the correct way, delta HF of HCOH. Put these values in, so that means I'm going to have minus 409.2 plus minus 393.7, which gives me a value of 15 something plus 15.5 kilojoules per mole minus 1. Okay, right, hope you managed to get that. Now we're going to go on to another example. So, using enthalpy change of combustion data. Okay, I'll let you have just a quick think about this, and then we'll go through the example, and then you'll have a go at doing the question. Okay, so using enthalpy change of combustion data. So if you're given enthalpy change of combustion data, we just go back up here, it probably means you're going to be calculating enthalpy change of formation. Which means if we go down here, which means that on the top it's more than likely to be an enthalpy change of formation. So let's pick something, C2H5 out, and it's formed from carbon, hydrogen, and I'm just going to leave the oxygen off at the minute. So here we have the enthalpy change of formation of ethanol from its elements in their standard states. We can add oxygen here. I'll explain why. I'm not going to bother at the minute. And once we've got this, we always have our combustion products on the bottom, so carbon dioxide and water. And we need to balance this up, so 2C plus 3H2O, so 2CO2 and 3H2O. Now in this example, if we're using combustion data, the arrows will always point down. And over here we can say that, let's draw the line, whoops, it's not a very good line, that CO2 and H2O are always on the bottom. Okay, so what that means is that, let's give this the value of, we'll do it properly. Okay, so we can say that my enthalpy change of formation, so my root 1, let's use a different colour pen, so my root 1 is equal to my root 2. So that means if I'm working out my enthalpy change of formation, I need to go from my elements to my intermediates to my product if I'm following root 2. These arrows are pointing the right way, and this is a combustion data, remember, so my definition for combustion is when 1 mole of compound is completely burnt in excess oxygen to form carbon dioxide and water, or whatever the products are. So here I'm going to have 2 times my enthalpy change of combustion of C. The arrows are going the right way. The arrow is going the right way here, so I will have 3 times the enthalpy change of combustion of H2. My arrow is now going the wrong way, so I will have minus my enthalpy change of combustion of C2H5OH. Okay, and then I can work out my enthalpy change of formation up here. Okay, so why do the arrows point down? Well, if we just think about the combustion data again, so if I do the combustion of carbon with oxygen, I'm going to produce CO2. This will be my enthalpy change of combustion. And again, like we were doing up above, all we're doing is writing it in a slightly different formation. So my carbon's here, and I form my CO2 down here. The reason why I haven't written the oxygen in up here, you can if you want to balance it out, is because it's already in its natural state and we can't combust oxygen on its own, combust with something else, because it's in excess oxygen. You can put the oxygens in if you want to, but you don't have to. So I'm going to leave them out for simplicity. Okay, hope that makes a bit of sense why the arrows are pointing down. All we're doing is taking this equation and putting it up here. Remember that the enthalpy change of combustion is for 1 mole of a species or product. So here I've had to times by 2 because I have 2 moles. Right, your turn. Okay, so have a read of this question, have a go, and then we'll go through it together. Okay, right, so answer following the question by drawing a Hess's law diagram. Calculate the enthalpy change of formation using the following data. Right, so I have carbon, hydrogen, and I have C6H6, which is benzene. So this is the compound, obviously. So that means I'm going to have my enthalpy change formation data on the top. It's a liquid. It's going to be formed from their elements in their standard states. Gas, then I have 6C and 3H2. I know that my carbon dioxide and water is going to go on the bottom. This is combustion data that we're using, so my arrows are going to point down. So that means, and then let's just quickly write it out. So this would be 6 of the enthalpy change of combustion of carbon, 3 times the enthalpy change of combustion of hydrogen, and this would be the enthalpy change combustion of benzene. So my enthalpy change of formation equals root 1, root 2. So these arrows are going the right way round, so it would be plus 6HC carbon plus 3HCH2 minus, this arrow is going the other way round, delta H combustion of C6H6. I can put these values in, as I'm sure you have done. So this is 6 times minus 394 plus 3 times minus 286 minus 3267. That's my arrows going the other way, which gives me a value of, what does it give me a value of? Oh, I haven't actually done the calculation. Right, so be back in a second, I'll do the calculation. Can't do it in my... Okay, back. I'd like to say I did it in my head, but I definitely didn't. I used the calculator, and it equals a equals plus 45 kilojoules per mole minus 1. Okay, so that is Hess's law. There are different methods to work this out, and I have chosen the method that I think is the easiest to understand. However, you may see different methods on how to calculate these. But I hope it was helpful, and I will see you next time. Okay, bye bye.